Hey everyone, welcome to the Explainer. Today we're totally cracking the code on IGCSE Physics 0625. And listen, the stuff we're covering today isn't just standard textbook theory. These are notes I've put together by literally reverse engineering the past papers. Every single checkpoint we hit is a literal exam point. To make sure these concepts sit in your mind forever, we're moving past static images to actually watch how a light wave behaves on its desperate journey to escape. It's going to be really cool, so let's dive right in. All right, here is your exact roadmap for today. We're covering 1. The rules of bending, 2. Anatomy of a wavefront, 3. Cracking Snell's law, 4. The critical angle, 5. Total internal reflection, and finally, Section 6. IGCSE hacks and applications.
So, Section 1. The rules of bending, or how waves react to boundaries. We start with the initial struggle. What actually happens when a wave enters a new medium and its speed suddenly changes?
Okay, these are your absolute foundational rules. Think of them like strict traffic laws for light. When a wave goes from a denser medium into a rarer one, say from water out into the air, it bends away from the normal line. But if it's plunging from a rarer medium into a denser one, like air into solid glass, it bends towards that normal line.
You can see this happening right here. Notice how that red ray on the left just escapes and bends away from the dashed normal line the second it hits the rarer medium. It's free to spread out. Now jump over to the right side. As it plunges into the denser medium, watch how it gets pulled in, bending tightly towards the normal. Away for rarer, towards for denser.
Now you might be wondering, why does it do this? Well, it's not magic. It physically travels slower in a denser medium because the particles are packed so much closer together, and that restricts the wave's movement. Oh, and keep this in mind for multiple choice questions. The bigger the speed difference between the two materials, the sharper that wave's going to bend.
Let's look at this a little closer. Section 2. Anatomy of a wavefront. Peering closer at the wave. Imagine these diagonal lines are like ocean waves marching forward. As the wave hits that boundary and enters the denser blue medium, part of it slows down first, while the rest is still catching up. See how those lines in the blue region suddenly bunch up together? That visual crunch you're seeing? That is the exact moment refraction happens. And that brings us to the golden rule for your exam. When a wave hits a denser medium, its speed decreases and its wavelength shortens. But, and honestly, this trips up so many people on the 0625 papers, their frequency stays absolutely constant. The source of the wave hasn't changed, so its frequency heartbeat doesn't change either. Okay, we know why it bends and what it looks like, but let's get into the math. Section 3. Cracking Snell's law, the math behind the bend. Here is your mathematical master key. Snell's law tells us that the ratio of your angles, sin I over sin r, is perfectly linked to the refractive indices and the wave speeds of the two media. It might look a little intimidating, but it basically just means the sharpness of the bend is directly tied to how much the speed changed.
Actually, scratch that. Before we move on, I have to give you a massive insider tip. Make absolutely sure your calculator is set to degrees for these angle questions. Seriously, if it's in radians, you'll do all the complex math perfectly and still lose the marks. Always check for that little D on your screen.
All right, we've reached the climax of our wave's escape attempt. Section 4. The critical angle, or the wave's breaking point.
What happens when a wave hits a boundary at a dangerously steep angle? Well, we're going to rapidly step through the 3 stages of a wave trying its hardest to exit from a denser medium out into a rarer one.
Just watch how this evolves from left to right. On the left, it refracts normally, bending away. But widen that angle and look at the middle ray. It hits a literal breaking point, the critical angle, and instead of escaping, it just skims completely flat along the boundary. Push it even further on the right and no way out. The wave bounces entirely back inside. Examiners love the formal phrasing for this, so let's define that middle stage. The critical angle is the specific angle of incidence inside a denser medium that forces the escaping ray to run right along the boundary line. The angle of refraction becomes exactly 90 degrees. And they will absolutely ask you to calculate this. You just use sin c equals n2 over n1. Oh, and if it's trying to escape into air, which has a refractive index of roughly 1, the math is super simple. Just sin c equals 1 over n. Easy. So let's dive into what happens if we push past that critical point. Section 5, Total Internal Reflection, where the trap is sprung. Boom. Look at what's happening right here. The wave is totally trapped. Because the angle of incidence is now greater than our critical angle, the boundary literally acts like a perfect mirror. 100% of the wave bounces right back down. The trap is sprung, and there is zero refraction happening.
You absolutely need to memorize these conditions because they trip everyone up. For total internal reflection to trigger, number 1, the wave must be moving from a denser to a rarer medium. Number 2, your angle of incidence, I, must be strictly greater than your critical angle, C. When you hit those two conditions, 100% of the wave reflects internally.
Okay, let's bring this all together. How do we actually use this trapped light? Section 6, IGCSE Hacks and Applications.
Remember how I said we reverse engineered the past papers? Well, this right here is the exact raw checklist the graders are using. When you're sitting in the exam hall, you need to be able to draw that clear wavelength reduction in a denser medium, and you need to state that at the critical angle, refraction is exactly 90 degrees. These are your literal scoring points.
And when they ask you for practical applications of total internal reflection, you can't just say it's shiny. You have to hit the specific list of modern technologies that graders are hunting for.
We're talking about things we use every day. We bounce light pulses down thin glass optical fibers to get high-speed internet. Doctors use it in endoscopy to safely look inside human organs without surgery. It's even the secret behind the prisms and binoculars and periscopes. It's incredibly useful.
So next time you see a straw look broken in a glass of water, or light bending through a window, don't just see a neat optical illusion. Ask yourself, is that wave speeding up right now or slowing down? Is it bending towards the normal or desperately trying to escape? If you keep these concepts visual in your mind, you won't just pass the exam, you'll truly master physics.